Learning goal number 20 is going to be all about writing expressions as a single power. So what we see sometimes is we have a power all by itself, and we can solve that, right, using repeated multiplication. But every once in a while, we're going to have expressions where we have powers that we can put together and join into one individual power. And today we're going to take a look at a couple of those ways that we can do that, a couple of laws that we have for that, and we're going to try to solve some questions based on that. Really, it's all about simplifying, and that's what we're going to be trying to do today. So when using powers, there are several different laws which we can use to simplify an expression. Okay, so we're going to be looking at how can we simplify an expression using certain laws. Okay. These laws are used to eliminate steps when solving an expression with powers. Okay, so we're going to be trying to eliminate steps when we are solving an expression with powers. Now, again, let's go through a little bit of review here. A power is a repeated multiplication expression, which is given using a base and an exponent. Okay. When we are using repeated multiplication, remember that the base is the value which is being multiplied by itself. By itself, and the exponent is going to be the number of times that it's being multiplied. Okay, so remember that we take the base, we multiply it, we're multiplying it the number of times that the exponent tells us to. For example, and the first example is written here, if we have something like 5 to the power of 4, and I've put into brackets, we don't necessarily need the brackets there, but I've put it in there. If we have 5 to the power of 4, this is 5 times, let's get into a formula here. 5 times 5 times 5 times 5. And we have 4 5s. And if we're going to, and again, that's writing it out in repeated multiplication. And this is just kind of a way of generalizing what it looks like. Okay. And we can also use this to solve. 5 times 5 is 25, times 5 is 125, times another 5 would be 625. Quick little mental math there. Trying my best. All right, so this is a way of solving it, and it's a way of determining what the answer or the standard form is going to be. Now, a power can be a part of a longer expression as well, and we can have multiple powers as well, and is then used as an operation in that expression, just like we did in learning goal 19, where we were trying to solve expressions using powers. Here it's going to be something very similar, but we're going to end up actually trying to find ways of simplifying things. So this one that we have right here, 3 cubed times 3. If we write it out in repeated multiplication, and I'm actually going to change all of these multiplying signs to a little dot, like that. And the reason I'm going to do that is because every single power I'm going to use the dots, and then when we're between powers, I'm going to use a multiplying sign. So that will hopefully help us to kind of differentiate between the two different pieces. So something like 3 cubed, for an example, this is 3 times 3 times 3, and then we multiply by 3. So 3 times 3 times 3 is 27. And then we multiply that by 3. And when we multiply that by 3, we're going to get 81 as our answer. Now, again, when we have bigger values like this, you can gladly use a calculator as well. But here I'm just solving, again, through order of operations. In the previous example, both of the values that are being multiplied can be thought of as powers. Now the first one I would consider to be quite obvious. Okay, that one's quite obvious. That's just 3 to the power of 3. That one's not overly difficult. But the second one also just has an exponent of 1, and therefore is kind of like here 3 to the power of 1. Okay, so we can kind of think of it that way. That doesn't fit in there overly well, but we'll try. Okay, so we can think of it as them both as being powers. And so what we're going to do is we're going to write that out in repeated multiplication. And we're going to write it, again, like I said, I'm going to use a multiplying sign for when we're going in a power, and I'll use, multiplying sign for between, like is in the example, and then I'm going to use a dot for when we are in a power. So 3 to the power of 3 is like 3 times 3, 3 times 3. And then we're multiplying that by 3 just by itself because it's just 1. Okay. Now, you'll notice that when the expression is written out using repeated multiplication, okay, it could also be simplified into a single power. Now, what do I mean by that? Okay, so I'm just going to, I'm jumping ahead a little bit here. It can be simplified into a single power. Okay. You'll notice that when we look here, we're actually just multiplying 3 together 4 times. Okay, we're not multiplying 3 together 3 times and then multiplying by 3 again. We're actually just multiplying it by like 4 times. So we could think of this 3 cubed times 3 could be the same as 3 to the power of 4. Okay? In fact, 3 cubed times 3 is 81, and 3 to the power of 4, well, let's just check this here on the calculator. 3 to the power of 4 is 81. Look at that, it gives us the same answer. Okay, so notice that the new exponent is just the sum of the previous ones. And remember, we're considering the second piece to have an exponent of 1. So 3 plus 1 is just 4. We're adding them together, and we get 4. And this brings us to the first law of exponents. Okay, when two, and so we're just going to kind of go through here. When two powers which have the same base are being multiplied together, they can be simplified as a single power with the same base as was original, okay, and an exponent. I'm going to slide it up a little bit, which is equal to the sum of the two exponents that we started with. So we'll notice here that 3 cubed times 3 is the same as 3 to the power of 4. 3, we'll notice that the base is exactly the same. Both of them have a base of 3. That has a base of 3. This one has an exponent of 3. This one has an exponent of 1. We add that together to get 4. Let's take a look at a quick little example here. Let's solve the expression as a single power. Now, normally we wouldn't necessarily have to write out in repeated multiplication. I will in this case. Okay, so if we look at it in repeated multiplication, we got 4 times 4, that's 4 squared, and then we have 4 times 4 times 4 times 4. Okay, so this is 4 squared, this is 4 to the power of 4. You'll notice here we have 6 4's being multiplied together, which means that this is the same as 4 to the power of 6. Okay, 4 is our base, 2 plus 4 is 6. So we can write it as a single power. We can do the same with negatives as well. Okay, so we can do the same as with negatives. In this case here, our base is -5, which is the same in both situations. So if we were to write this out as a single power, we would have a base of -5. We add our exponents together. We have 7 on the first one. We have 3 on the second one. So our final exponent is 10. So we can simplify this to -5 to the power of 10. And again, if we were to solve for -5 to the power 7, and we were also to solve for -5 to the power 3 and multiply them together, we would get the same answer as if we have -5 to the power of 10. Quick little note though, we have to remember that this only works, okay? It only works if the powers have the exact same base. So it only works if they have the exact same base. If the bases are different for whatever reason, okay, so if you're given an operation and the bases are different, okay, this law does not apply. And then you can just solve it the way that we would have with order of operations. We can't actually put them together.